This is Physics 1, Chapter 7 on momentum, and this will be part 1. And for momentum, what we're talking about is a mass that is in motion, or a mass that is moving. So mass M moving at speed v, or velocity v. And to find the momentum, which is labeled as a p, is just mass times your velocity. Okay, kind of very simple here. Just two things you gotta multiply. The units of momentum follow the equation, kilograms, meters per second. Or if we multiply this by second over second, we get kilograms, meters, second squared times second, which is a Newton second. So we have a couple units you can use. This is the kind of the quicker way of writing the unit. This actually follows the equation, so it's probably the easier one to remember. Either one is fine. We don't make up a new unit for momentum for some reason. So for momentum, if we have a larger mass, we have a higher momentum. If we have a larger velocity, we have a higher momentum. So if we increase the mass, we're increasing the momentum. If we increase the speed, we're increasing the momentum. Another way of looking at this is if the mass is 3 kilograms moving at 1 meter per second, it has a momentum of 3 Newton seconds. If it's 4 kilograms moving at 1 meter per second, then it has 4 Newton seconds of momentum. At the same time, if it's 4 kilograms and it's moving at 2 meters per second, then it has 8 Newton seconds of momentum. So, you compare these two, higher velocity, higher momentum. If you compare these two, higher mass, higher momentum. And of course, if you compare this one to the first one, you're definitely going to be increasing your momentum because you're increasing both factors. If the speed is 0, you get a momentum of 0. Okay, so this is when it's at rest. There's no momentum. This actually becomes very important because during our problems, they will tell you if something's at rest or stationary or not moving, and you actually do know the momentum even if you don't know the mass. So let's get to example. We have a green billiard ball and we have a purple one. And the green billiard ball has a mass of 0.1 kilograms, and so does the purple one. The green one has an initial velocity of 0.5 meters per second, and the purple one has let me put P here for these, has a velocity of 0 since it's at rest. So the momentum of the green one is 0.1 times 0.5, which is 0.05 Newton seconds. Momentum of the purple one is 0.1 times 0, which is 0 Newton seconds. Okay, so simple calculations, if you know the mass and the velocity of an object. Alright, so what's going to happen is that purple one's going to hit, the green one's going to hit the purple one. And after it hits, you're going to have different speeds. So this is going to be after the collision. This is going to be before the collision. This is going to be the collision. This line I'm going to draw. After, neither one's going to lose any mass. the purple velocity gains 0.5 of the speed. So velocity of the purple is 0.5 meters per second, and the green one stops. So velocity of the green one is 0 meters per second. So now the green one is 0.1 times 0, which is 0 Newton seconds, and the purple one is 0.1 times 0.5, which is 0.05 Newton seconds. What we have here is a collision, and we see that there's a change in momentum. Okay, and there's two ways of finding this change in momentum. You can find the change in momentum by doing the final momentum minus the initial. So for the green one, the final was 0 minus 0.05, and you get negative 0.05. For the purple one, the final was 0.05 minus 0, and you get 0.05. It's no accident that these two have equal but opposite momentum. Okay. What I want you to think about is when we have these two billiard balls and they collide. This one's going to be the green one, and this one's going to be the purple one. Purple one is putting a force onto the green one. The green one is then putting a force onto the purple one. And by Newton's third law, the forces are equal and opposite. Okay. So how does this deal with momentum? Well, that'll be the next thing we get into, is that change in momentum is also called an impulse. And that impulse deals with force. So if you have a momentum change, that means you either have the mass or the velocity changing. If the velocity is changing, it requires an acceleration. Matter of fact, if the mass is changing, it's going to require acceleration. And so the acceleration requires a force. So impulse requires a force. And what we actually have here is that impulse is what's found to be force times time, which follows this unit, newtons times seconds. And so, based on Newton's third law, if that force is equal and opposite, then let me write out the let me get myself some space here. The green ball has a momentum of 0.05, that's negative, equals some force times some time of collision. And the purple ball has 0.05 equals some force times some time of collision. This collision has to be the same time. I mean, they interacted with each other. That has to be same time. Matter of fact, that means the force itself in magnitude has to be equal. Which means the only thing that's not equal is the fact that there's a negative sign, and that's because the forces are equal and opposite. Alright, so when it comes to impulse, we have the fact that if you have a specific impulse, then the shorter time requires a larger force, and a longer time requires a smaller force. So let me give you an instance, and this is the one I tend to go with is we have a person here, and he's boxing, and There's another person, and he's going to be throwing the punch. And so he's throwing a punch. At that guy. Okay? And I'm going to make the glove red. Most boxing gloves I see are red. Okay. Now, we have three things here that we're looking for. The change of momentum. Oops. Change of momentum, the force, and time of collision. Okay. Which one can this guy control? Well, he really can't control the change of momentum. That's going to come from this guy. This guy has complete control over that change of momentum, because what he's going to do is his glove's going to start out with a momentum of 0, and that's going to be your initial momentum. So I'll put a little I. His final momentum is going to be the mass of his fist times the velocity of his fist. And so he has a specific change of momentum that he's going to hit with this guy. And so it's going to be a specific impulse that he's going to send into this guy. Well, all this guy can do is either stand there and take a quick jab, which is going to have a short time. And if he takes a quick jab with a short time, he's going to have a large force, and he's going to feel it a lot more. So what he's going to do is he's going to do what's called ride the punch. And he's going to lean back, go with the punch, make sure the contact goes long, and so the force ends up being short or low, for that matter. Okay, to reduce how much force he ends up having on him. Right, so in the previous example, we had a impulse of 0.05 because that was the change in momentum. Right, from green ball to purple ball, that was your change in momentum, 0.05. And we want to know the force if it happened over 5 milliseconds, so 0.005. Okay, so the force is 0.05 over 0.005. And you get 10 newtons. Okay. Now, what if we do it over 1 second instead? And so you have that change of momentum, 0.05 equals the force over 1 times 1 second. So the force is equal to 0.05 newtons. Okay. A lot higher over time, a lot lower of the force. Okay. So the reason, or the question is, what happens if, the momentum change wasn't equal and opposite? Well, it can't happen. So it's actually kind of a simple answer. It can't happen because we have what's called conservation of momentum. And so if an object, like the green ball, loses momentum, the momentum must be transferred to another object. And so the purple ball gains that much momentum. Right? And that doesn't necessarily mean that it's going to lose all its momentum. So let me give you an example. Let's say we have a pool table. With the pockets here. And you're going to hit this white ball into a green ball. Okay. Now, if you hit hard enough, this green ball will go, that white ball will come to a stop. Matter of fact, let me put this where it should be. This always seems to happen. You have the white ball there, and you have the green ball along the side. So you hit this, and if you hit hard enough, that white ball comes to a stop. All of its momentum gets transferred to the green ball, and the green ball goes in the pocket. If you hit too softly, that white ball hits the green ball, transfers a little momentum, they both roll together into the pocket, and you scratch. Okay, and so this is what I mean by, it doesn't have to lose all its momentum, but any momentum it loses must be gained by another ball or another item. So force causing any impulse will cause a transfer of momentum. Momentum cannot be created or destroyed. It just transfers from one object to another based on the external force. Now, in the absence of an external force, the momentum of the system must remain unchanged. So let me demonstrate what I mean by external force and not having an external force. Let's say I have a pool stick, and I'm using that pool stick to apply force to the white ball. Well, in the contact between the white ball and the green ball, that is not including an external force. The external force will be the force from the pool stick onto that system. Another idea is if you have an astronaut, and you see they're out in space, and they kind of get stuck in a little away from the ship, so they throw like a hammer in the opposite direction that they want to go. Alright, so I'll do it this way. Astronaut in space. He has a hammer. Best hammer I can draw. And he wants to go, let's say he wants to go this way. Here's the spaceship. And he wants to go this way, but his rope got cut, so he can't get to it. So right now his momentum is 0. So he throws the hammer this way. That's where the hammer goes. And he goes this way. So the momentum stays 0. And then he'll keep going until he hopefully reaches that ship. Alright. Doing a lot of drawing today, I guess. Alright, so we have a couple kinds of collisions. We have elastic. These objects collide without deformation or generation of heat. Momentum is conserved. And so by momentum is conserved, we have P1, actually no, hold on a second. P1 before the collision, so I'll put B there, plus P2 before the collision equals P1 after plus P2 after. And then M1, well, I'll get to that in a minute. Okay, so that's what that means. The next one is kinetic energy is conserved. This means K E1 before plus K E2 before must equal K E1 after plus K E2 after. Okay, so both of these two equations have to remain true. Which means for the kinetic energy you have 1/2 m1 v1 squared plus 1/2 m1 v2 squared, and I'll put little b's here for before, equals 1/2 m1 v1 after squared plus 1/2 m2 v2 after squared. This, which is this equation, and this has to remain true for it to be elastic. For it to be elastic, the momentum also has to stay true, which means m1 v1 before plus m2 v2 before must equal m1 v1 after plus m2 v2 after. Now this is for elastic, and for inelastic, only these two have to remain true. These do not. This is only for elastic. Okay. For inelastic, the kinetic energy is not conserved. Energy is still conserved. That energy is transferred into other forms, usually sound from and breaking from deformation, generation of heat, things like that. Now, when two objects collide and there's inelastic, they can have what's called perfectly inelastic or completely inelastic. And these, when they collide and stick together, and so what happens is they will combine and travel with each other at one single velocity. Kinetic energy is still not conserved, right? So it's still inelastic. But what this means is this V1 and V2 after are actually the same thing. So you actually will have V1, M1 V1B plus M2 V2B equals M1 V1 or VCA is what I'll call them combined afterwards plus M2 VCA. These are the same, so we factor them out and you get M1 plus M2 VCA, and so they combine. It actually makes the math a lot easier. So let's do an example. You have two carts. First cart is at 4 kilograms and 3 meters per second. The next cart's at 6 kilograms and 3 meters per second. Now notice one cart's going one way, one cart's going to the right, one cart's going to the left. It says that they stick together afterwards. So what we can do, we can look at these carts. Mass 1 is going to be 4 kilograms times 3 meters per second. Mass 2 is going to be 6 kilograms times a negative 3 meters per second. It's going the opposite way. We have to make one of those velocities negative. That will equal m1 plus m2 times the combined velocity, okay, which m1 plus m2, I should just write that in. That would be 10 kilograms. Okay. So this becomes 12 plus a negative 18 equals 10 VCA. And so negative 6 equals 10 VCA. So the velocity after for both of them is going to be negative 6 over 10 or negative 0.6 meters per second. So it's going to go to the left together and be combined together that kind of drew bad, but combined together going at a speed of 0.6 to the left, okay, after the collision. Okay. The next problem is a bit harder because it's elastic. And trust me, I've struggled with this a few times, and I've done it a few times, but there's little parts that can easily be missed. Okay. So we're going to have this where it's two elastic collisions. Now we have the first one set up. That's the momentum. 4 kilograms times 3 plus 6 times -3 has to equal the momentum of the mass of 1 times velocity of 1 after, which we have the initial momentum, so I'm just going to leave off the after, just to not to write so much, plus the momentum of 2 times velocity of 2 after. Right, so we can say that this is going to be 12 plus a -18 equals m1 v1 plus m2 v2. So -6 equals m1 v1 plus m2 v2. So this is the momentum part. Now we'll go get into the kinetic energy part. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And so we can do some of the math. Now, before I forget, there is one thing, and this is what I always realize is the mistake I make. These velocities after are not going to be positive. And the way it ends up turning out is actually this mass 1 ends up being negative. Okay, it ends up bouncing off of this and going to the left. Because these are elastic, this one's going to bounce off and goes to the right. So they're not going to go through because they'll be going together and be inelastic. So they have to bounce off of each other. So they have to have different signs on this side. Right, so this is one of the easiest things to make a mistake on, is knowing this one's going to be going to the left. Now, in the kinetic energy, it doesn't matter because you're going to be squaring it. So now we see 1/2 times 4 is 2, times 9 is 36, plus 3 times 9 is 27. Okay, just want to check my math there. And that's going to be equal to 1/2 times 4, which is times v1 squared, plus 1/2 times 6, which is v2 squared. So this is, let's see, something's off about that. I don't know what. I don't know. Something looks off for some reason. 2 times 9. Oh, that's why I did 4 times 9. 2 times 9 would be 18. There you go. That makes sense. That's what I wanted to see. And then this would be 2 v1 squared plus 3 v2 squared. And then up top here, we have -6 minus 4 v1 plus 6 v2. Okay. So what we can do is we can solve for one of these and plug into the other one. So if we solve for, say, which one did I solve for? v1. So -6 minus 6 v2 equals -4 v1. And then multiply the negative sign over, that makes these all positive. And so you get v1 equals 6 plus 6 v2 over 4. which is going to be 3 plus 3v2 over 2. Okay, so now I take this one and I plug it in for the first equation. So 45 equals 2 times 3 plus 3v2 over 2. Now v squared plus 3v2 squared. Alright, so what I'm going to do, let me give myself more space now, is I'm going to do this part separate. So 2 times 3 plus 3v2 over 2 squared. That is going to be the same thing as 2 times 3 plus 3v2 over 2 times 3 plus 3v2 over 2. And so this 2 is going to cancel with that 2. And so you have a 1/2 on the outside. And then we can multiply these. And what you get is 3 times 3 is 9. Plus 3 times 3 here is 9v2. Plus 9v2. Plus 9v2 squared. I'll rewrite that here in a minute. Okay, so let me put all this together. 9 plus 18v2 plus 9v2 squared over 2. And that's going to be that part of it. That's going to equal 45, and you have this 3v2 squared. So now what I want to do is multiply by 2 across the board. So I get 90 equals 9 plus 18v squared plus 9v2 squared plus 6v2 squared. The 2 that would multiply this cancels out with that 2. So I can put all this together. I'll subtract the 90 over as well. So this is going to be 0. I will have 15v2 squared plus 18v2 minus 81. Now I have to use the Pythagorean theorem. So v2 is going to equal 18 plus or minus square root of 18 squared minus 4 times 15 times 81, which is negative, so that's going to make it positive, over 2 times 15, which is 30. Right, so 18 plus negative 30. Let me figure out what's in the radical there. 18 squared plus, let's see, 60 times 81. We have the 60 from 4 times 15. So 5181. Okay. So let me take the square root of that. So square root 5184. I get 72. Works out nicely. So I get 18 plus or minus 72 over 30. Okay. We can probably reduce that down. If I divide by 6, I get 3 plus or minus 12 over 5. And so I get 2 possible answers. First one, 3 plus 12, which is going to be 15 over 5, which is going to be 3. Second one will be 3 minus 12, which will be negative 9 over 5, which is going to be a negative 1.4. Let me just double check my math here. just want to go through, make sure I have everything right before I keep going. So when I square that, 9b squared. So 918, 9. I don't see anything wrong so far. Oops. So let's go to V1. We know V1 is 3 plus 3 V2 over 2. And we're going to put in V2, so we get 3 plus 9 over 2, which is going to be 12 over 2, which will be 6. Alright, and then that's one possibility. The other one is 3 plus 3 times negative 1.4 over 2. So negative 1.4 times 3 plus 3 divided by 2 is negative 0.6. Alright, so let's see. V2 I said was supposed to be positive. So we should have a positive value here. And then that should lead to, we're putting in 3 for V2, a positive value for V1, which will be 6. Okay, so those should be the right directions. So let's try these now. This should equal a negative 6 when we find the momentum. So this will be 6 times 4 plus, actually, negative 6 times 4 plus 6 times 3. That would be a negative 24 plus 18, which is negative 6. Alright, and so that's that. And then, let me see what the time is. Okay. And so we do, we can check the kinetic energy, 1/2 times 4 times negative 6 squared, which is going to give 2 times 36, which is going to be 72. And then this will be, it's already really high. 6 times 3 squared over 1/2. It's 3, that's supposed to be 3 squared. Yeah, 9, 54, 27. Which gives 45 when I subtract them. Why am I subtracting them? Oh, let me see why I went wrong. I had to have gone somewhere wrong with this. As I said, this can get so complicated within the math. So I have 6 over 4. Well, you know what? I'm gonna look this out off camera, and then I'll come back and I'll start here, tell you what I did wrong, if I find what I did wrong, or I may redo the problem, and we can see what happens. It's probably a sign error, because it seems like that's what's happening here. 72 and 27 should subtract 45, but I don't have any reason to subtract them, so I'm trying to figure out why that's happening. Okay, so I'm going to stop the video here, and we'll continue with this in the next video.